And one of the topics that always has blown my mind is the notion of locality in this quantum entanglement and, these claims that spooky action at a distance, all this kind of stuff. So that's why I end up doing research on it. And that saves you from this Bell theorem, and you can reconstruct a very coherent, very nice picture of quantum mechanics where everything is local, everything is very well understood. It has some caveats. You need to watch the rest of the video to understand the caveats. But overall, quantum mechanics can be considered local, and you can describe entanglement through just local interactions and local properties of the particles involved. And in my PhD, basically, I looked at this interpretation of how to save local realism in quantum theory, and I just wanted to make sure that it worked for all quantum systems. And that's it.
Hi, I'm Maria Villaris. I'm a PhD student at the University of Oxford researching the foundations of quantum information. Welcome to my podcast on the foundations of quantum physics. Today I'm joined by Nicetu Tibau Vidal. Nicetu was a PhD student in my group some years ago, and now he's doing a postdoc in Hong Kong. And I've invited Nicetu here today in particular to talk about the topic of locality, which has loads of interesting implications for quantum physics and is often expressed and communicated in confusing ways. So we're hoping to clarify some of those ideas in this conversation and find out a bit about the research that Nicetu has been doing on this topic and kind of hopefully upgrade all our understanding of what the latest ideas on this topic are. So thanks for joining, Nicetu. Would you like to just introduce yourself to our audience and tell us a bit about your background and how you got to the point you are today?
Sure. Thanks, Maria, for inviting me. Thanks for thinking about me to record this podcast. Basically, I studied maths and physics in Barcelona. Then I came here in Oxford to do my master's degree, and I've always been very interested in the foundations of quantum theory. So probably as some other members of our audience, in high school I got addicted to science communication videos and books on quantum theory, and all these claims that, quantum theory is so weird, quantum theory is, it's very difficult to understand, just really made an impact on me, and I really wanted to understand it at a deep level. So then when I was here in Oxford, I met with Chiara Marletto and Dr Vidal, which are our supervisors, and I saw that their approach and their research was based precisely on this, on understanding quantum physics better. And one of the topics that always has blown my mind is the notion of locality in this quantum entanglement and, these claims that spooky action at a distance, all this kind of stuff. So that's why I end up doing research on it.
Cool, thanks.
All right.
And how did you kind of come across Chiara and Vladko's research when you were here?
So, that's a very good question. Actually, so in the masters that we did, it is required to do a dissertation. So my interests were more towards quantum gravity and the connections with quantum information. So
because you did like a dissertation on the black hole information paradox before.
Yeah,
right.
Exactly.
And,
On my bachelor's thesis was about that. And so basically I scoured all the Department of Physics and Mathematics of people who worked on this similar topic. And then I came across this very nice work by Chiara and Vladko on the VMB experiment. Maybe some other video you can do it about that.
Yeah, it's a good idea.
That's cool. And which basically it's the interface between quantum information and quantum gravity. So it seemed kind of a perfect fit to do the dissertation with them.
Yeah, cool. And I'm just curious, were there, because I also kind of got excited about quantum mechanics from high school popular science reading things. Are there any examples in particular that stuck out that, books or articles or 100%. Videos or anything?
Minute Physics. Shout out here.
Cool. We'll put a link
Amazing.
in the description.
Exactly. Amazing channel. I was just mind blown by it. And then, basically I'm from a small village in near Barcelona. So the amount of resources and books that you can get on science communication is not super high. So every time I just found a book that seemed good quality, I just read it, but they're not kind of canonical. Or later you grow as a physicist and you're like, okay, it was a bit random that I read this.
Yeah.
Yep.
Yeah. Cool. Great. So, yeah, that's a good introduction. And could you also just, tell us a bit about what you're doing now? So you're based in Hong Kong now?
Yeah. Now I'm based in Hong Kong since October, when I finished my PhD, which the topic was on locality of indistinguishable quantum systems. So now I'm following a bit the research that I did in the PhD, and that we will talk a bit in the podcast. But I'm also trying to gravitate more towards quantum gravity, work on the black hole information paradox. Exactly. I want to gravitate towards quantum gravity, exactly. The black hole information paradox.
Yeah.
And even now we are trying to implement some of these crazy models of indefinite causal order and this kind of stuff, but
maybe also
we want to do it in the lab. Yeah.
Another podcast.
Exactly.
You want to do it in the lab.
Yeah.
And it's a quantum optics lab, right? So
quantum optics lab. So
photons and
stuff. We will align a lot of mirrors, use some crystals to generate entanglement. So it seems very exciting.
Yeah.
Very
cool. Yeah, lots of cool stuff. But so today, we're going to talk about locality, which is the topic that you also did in your PhD. So maybe to get started. So I should also say our plan is to kind of have two parts to this podcast. One part being explaining this topic in a way that's generally accessible, so not using the kind of specialist language or specialist mathematics, and kind of trying to explain it in a very broad, accessible way. And then doing a kind of more technical deep dive for people that have taken some kind of course in quantum mechanics and understand the formalism, are familiar with the technical aspects, and be able to kind of explain the ideas more concretely for people that have that background. So hopefully both parts are useful for some people.
I'll try my best, but I hope you help me achieve the nice communication spot. Yeah,
between us we'll do our best. And if you have comments on how well that format worked, or if it needs if there are ways that it could be improved, do let us know in the comments.
Perfect.
Yeah, great. So to start with, could you just kind of summarize what is locality? Like, what does the word mean? What is the idea?
Okay. It's a very difficult question to answer. That I would say that locality is kind of a concept, right? Let's say it's a principle. What I mean by that is, in physics, you guys may know, we have laws of physics, right? So we have behaviors of the natural world that we want to describe. All right. However, you could see some behaviors always follow a certain pattern. So that's when we call principle. Maybe you've heard of the principle of conservation of energy, or the principle of conservation of momentum. So one of these principles, it's a principle of locality. So this is to define the category first. Okay?
Yeah. So it's like a very general law of physics.
Yeah.
It's like a way of saying what a principle is.
Exactly. Yeah.
Yeah.
Yeah, it's very good. Nice to say it. Exactly. And it's a word that explains very well what we mean, because it's usually in the natural language, like we know what local means versus locality, like
we
your
use it
local
in an everyday
council.
sense.
Exactly.
Like, yeah.
And basically it's
the local Tesco or supermarket or whatever. Yeah.
Exactly. So, and what this word refers to is to the fact that you have space, let's say, and that your property or anything you're talking about is localized in that space, so that it's not spread throughout the entirety of your system, but that it's particular to a concrete place in your system.
Yeah, so it's like you have your local supermarket that's close to you, it's localized in your town or
vicinity or
where
neighborhood.
you are, as opposed to like a distributed supermarket that's far away. And yeah, locality refers to this close region.
Exactly. However, in physics, how we use it in physics, the principle of locality. So since there is this general idea, there's different meanings of the word locality within different contexts of physics. But most of them basically refer to the same idea, even though the formalization, it's the devil is in the details, let's say.
And we'll go into that later in more detail.
But basically the idea is that we have a space, right? And we want to describe how things move in this space. And basically the idea is that you can localize things in space, so that when I talk about this iPad or this glass of water, I don't need to talk about all the universe to talk about this glass of water. So that this glass of water is kind of independent entity of the rest of the universe. That is the first aspect of it, so that you can just talk about individual stuff, which is a part that sometimes it's neglected. And
so you can talk about the glass of water without referring to the property of like the box or something else.
100%. That's the first thing.
Or Andromeda, slightly further away.
Exactly. The second thing is that what you want is that this glass of water, in order to, if it happens something to it, right? That's something to it, if I want it to affect that glass of water, it needs to be kind of a mechanism of interaction that is local. What do we mean by that? What we mean is that this glass of water, in order to, spill the other glass of water, needs to get close to it. So it can get close to it either by moving there and just bouncing. Let's say, let's do it, Cheers. A bit bad luck, that's the truth, but sorry. So either we do that, or there is some other stuff in between that mediates between the two. All right. So for example, let's say that we would have a big pole here, right, between the two. So you can knock the pole here, and then the pole would move, and then it would hit the other glass of water. So that's the local behavior of physics. So basically the principle is that we don't expect that if I move this glass of water here, a coconut will fall in Costa Rica. All right?
So it's like things that are separated in space can only affect each other if they directly interact. Through either like directly those things interact, or something in between them is like directly interacting until it gets to that thing. But something physically has to be
carrying that influence, let's say. That's locality for you.
Cool. So that's what locality is. So so now thinking about it in the context of quantum physics, so the kind of usual the reason, the thing that comes up a lot in quantum physics is non-locality, and the kind of standard storyline that you'll read in popular science or even physics textbooks, just science, is that there's this phenomenon that happens in quantum mechanics of entanglement, where you'll have two, which essentially is saying that if you have these quantum systems that are separated in space, then it seems that there's some non-locality in the sense that maybe doing something to one system instantly influences the other one from a distance somehow. And it's this is related to the experiments that won the Nobel Prize a couple of years ago, the Bell tests that are kind of often communicated as showing that reality behaves this way, that there are these instantaneous influences from when two systems are quantum entangled.
Yep.
And it's also often said that kind of Einstein didn't like this, and Einstein was wrong because he thought that locality was a really important principle. Maybe what's good to, before we dive into all the what does entanglement mean, what do the Bell tests tell us, so yeah, we'll explain what those are more. Maybe we should talk about kind of Einstein's idea of locality and why it's relevant for physics theories, why it's an important principle for physics.
Makes sense. The principle of locality goes way back. So even when Newton was developing their theory about universal gravitation, they were very concerned about gravity. About locality. Because sorry.
He was concerned about gravity,
yeah, he was concerned about gravity. And especially like in his fights with Robert Hooke, it's a concept that it was very present in even those days discussions. So for example, there is a famous experiment of Hooke that basically is the synchronization of two clocks, because for navigation in a boat, they needed to know what was the time back in London when they were in the boat. It was important for them to calculate where in Earth they were was for navigation. So then there was this design by two pendulum clocks, right, by Hooke, that they would hang from a bar, the two clocks, right? And what Hooke saw is that if you would move one of the pendulums, right, but then let the other still, if you let it evolve over time, both would be synchronized. And this was very puzzling to him, because it's like, this is very far away from this, so how is the movement of this pendulum synchronizing with this other one, right? So what Hooke tried, back then theorists did a lot of experiments as well, so that's good. So they put, they said, well, maybe it's the air current, because the pendulum is heavy, so maybe like it's blowing the wind and it's making the other pendulum move. But then, very smartly, he put kind of a barrier, so the air would not flow, and he would observe the same phenomenon. So in the end, he ended up deducing that he took the hanging bar of the two pendulums, and when he took the bar, the effect was not there. So in the end,
when he removes the bar, and
exactly,
yeah.
Did I explain that correctly?
Yeah.
Okay, sorry. So then he realized that the bar was mediating the vibrations of the clock to the other one. So it was a very important property that was discussed and discovered back then. Also, the main reason for the debate in the universal law of gravitation was that it was non-local. What do we mean by that in this specific context? What we mean is that Newton's law, basically, if you follow Newton's law, maybe in our audience people have taken some high school course and they have the gravitational potential. What you see is that if the sun suddenly disappears, right? What Newton's law predicts is that immediately, it doesn't matter that the sun is so far away, that immediately when the sun would disappear, we would stop our rotation over the sun. Right? So this we feel it's non-local, because we feel that
instantaneously.
It's instantaneously. So
something happening over here
has an immediate
disappearing
effect. Exactly.
Has an immediate effect on the Earth, which stops going around.
Exactly.
All
right. Exactly. So if gravitation would be local, what we would expect is that when the sun disappears, it would think a bit of time for that information to be carried to the Earth, and then the Earth, after some time, it would stop
like
orbiting
8 minutes
the sun.
or
Exactly, 8 minutes. So this gave the idea basically to Einstein to say we need to fix gravitation.
So before that, were people kind of worried about it, but
Yeah,
were kind of just didn't really know what to do about it?
very
Or like-
much. No, there were a lot of theories. Like it was a very big problem in the 19th century, because so they had all of these theories about ether.
Yeah.
Maybe you've heard of that.
Yeah.
Maybe the audience as well.
Yeah.
Yeah. So basically, the thought process was, well, if there's vacuum between them, so maybe we need kind of this material that propagates this influence, but in a very, very fast way. So maybe it's not immediate, but like in a very fast way. So there were like all of these theories to try to fix it. However, Einstein took a more kind of radical approach, and he said, no, let's put locality on the center. He also did that. Sorry that we are doing a very long history of physics. You can cut that out later if you want. Sure.
Some people like history.
Okay, that's good.
I'm interested in.
That's nice. So before Einstein, there was Maxwell. And Maxwell, it's sometimes underappreciated. So Maxwell solved basically he unified the laws of electromagnetism, but not only did that, but he also was a very strong advocate for the notion of field. And the notion of field, basically what it does, is to precisely have this idea that you have something that you cannot see, but that it's physical, that it exists, and that it mediates these interactions between the particles. Because before Maxwell, people didn't exactly believe in fields. People believed in forces and in particles. So it's slightly different, because the picture before is like you have some charge here, you have some charge here.
Yeah.
There is a force that this charge affects on this one.
Like instantaneous.
Exactly.
Force.
Exactly.
Yeah.
Kind of instantaneous, but sometimes no. Like
Okay. Yeah.
it's
like,
just
not necessarily.
yeah, but you just didn't think about that. It's just some interaction that happens, and sometimes it comes with a delay, but it's just an interaction.
Yeah.
But what Maxwell did is like, no. What actually is going on is like you have the charges, but then there is this invisible thing that we called field. Yeah, maybe this is a very technical physicist word, but basically it's kind of it's a mathematical entity that fills space, and that it propagates interactions and mediations between particles. That's what a field is. So then Maxwell said, no, these fields are there, kind of the electric field or the magnetic field. Magnetic field, quite famous.
Yeah.
So then the mechanism, it's not, this moves and it makes this influence here. It's this moves, disturbs the field. The field moves in a specific way. And then when the field, kind of like a wave in the sea, hits the particle, then you see the influence of the particle there. So that changed radically the vision towards locality. But this was Maxwell, which was, sorry if I get it wrong, I think it's late 19th century. And then everybody was kind of very satisfied with this explanation.
Yeah.
And then Einstein basically took it and tried to apply it to gravitation. First, he developed all of the special relativity, where this concept that the speed of light, it's a universal limit for these mediations happening. It's quite important. And then he developed general relativity with this idea that gravity has to be local as well.
Yeah.
Okay.
Yeah. So locality was a kind of fundamental principle for developing special relativity and general relativity.
Exactly.
Yeah, okay. So now let's think about what happened when kind of quantum mechanics got involved.
Sure.
And so then we have this possibility of quantum entanglement. And like I mentioned earlier, it's kind of a situation where you'll have your two particles will kind of interact by some quantum interaction, then you separate them, and then the story goes that they seem connected in some extra quantum way.
Yeah.
So, can you talk a bit about what troubled Einstein about this, and what kind of what seems troubling about quantum entanglement?
Sure.
Yeah,
makes sense. So we need to be a bit clear that correlation is not weird, let's say. So, for example, this is a very typical example, so some members of the audience might know it, is imagine that I was a very weird physicist. It's a very wild speculation. And I would always wear socks that are different color. Okay.
I think lots of people do that. But yeah.
But you are 100% sure that I will always wear socks different color. Okay. So then, if someday I work in the office, but I only put one of my 2 feet, and you see the color of my sock, you can immediately deduce that the other sock will be of a different color. Does that mean that you looking at the color of the sock, you made the other sock be a different color? No. It just means that there was a pre-existing condition between the 2 socks, that is that I am a weird physicist, that is prepared in such a way that you expect this property to happen. Okay?
Yeah.
So this is very important, that the fact that you can deduce something immediately of something that is far away, that is not weird, that is not non-local, that is just induction of or deduction of some reasoning.
So when 2 things are fully correlated, look at one, you can instantly know what the other one is because it just was prepared in that property. Yeah. Exactly.
Some other examples, it doesn't matter. Okay. Can you repeat the question?
So the question is kind of what seemed troubling about quantum entanglement.
Sorry. What seems troubling about quantum entanglement is the fact that you have this coupled with the fact that the answers seem random. So that when you look at the sock, sometimes it will be black, sometimes it will be white. Okay? And that these two always agree. Okay? So when you couple these 2 things, it is more troubling. Does that make sense?
Yeah. So it's like you, it has like a random chance of looking one colour or the other colour, but the colours are always correlated when you look at them, and so there's this kind of additional correlation from what you get with normal socks, normal classical physics.
So, but specifically, what is troubling, and this is what Einstein, like it's always Einstein, what Einstein in 1935 said is like, if you think that quantum mechanics is the whole story, let's say, that you do not have extra elements in your theory, that is just quantum mechanics as it is, exactly. Then, what is especially troubling about quantum mechanics is this randomness, okay, that we have talked about. But this randomness, you can also have it in quantum physics, in classical physics. So the Stokes example,
like a probabilistic.
Exactly. Imagine
physics.
me before leaving the house. I'm a weird physicist. I only have black and white socks, but I flip a coin of whether if I put the white sock on my left leg or if I put it on the right leg. So that is still probabilistic, right? And we still don't think that if you see my left sock being white, that you can know immediately that my right sock will be black, right? So there is an extra element to it, which is that in quantum mechanics, what is very weird compared to classical physics is that when you do a measurement, you need to disturb the system in a very radical way. So, for example, if you want to measure the trajectory of a ball, the only thing you need to do is to shine some light to it and that it bounces back, so then you can see where it is. But you shining light to the ball will not perturb the trajectory of the ball.
Yeah,
right?
It does the same thing if you hadn't shone that light
Exactly.
as if you had.
Exactly, because the interaction it's very minimal, let's say. However, in quantum mechanics, the distinct property is that systems are super coupled together. So that if you want to measure a property of a quantum system, you need to interact very strongly with it. Because otherwise you cannot extract that information. And when you interact in that strong way, you are kind of destroying the previous, you're modifying the behavior of your physical system. Okay, so that is the striking part, because now in the SOX scenario, right, in quantum physics, let's say we don't have systems that only have one property, kind of the color of the sock. We have the Heisenberg uncertainty principle, where sometimes if you want to measure one property, you cannot measure the other one. All right, so with all of these elements together, in quantum physics, in our silly example of the socks, basically is that, for example, you could not measure at the same time the color of the sock and, I don't know,
size,
and the size of the sock, or how many holes does it have, or you could imagine something like that.
Yeah.
Okay, but with a quantum particle. All right. So then it appears that when you choose to measure that property, right? So let's say Maria is going to look at the color of the sock, right? But then the other person that is looking at my right leg, at my right sock, decides to also measure the color of the sock. So there is this aspect of free will of the observers that then makes still their answers are always correlated.
So we have like two observers that will each look at one of these socks.
Exactly.
And they can either look at colour or look at number of holes in the socks.
Yeah.
And they have this kind of free choice as to whether they're going to choose to look at the colour or choose to look at the number of holes.
Exactly. And every time they measure the same property, their answers will be the same. And that is the striking part, because then if you try to reproduce this with socks, you'll see that the only possible answer to this query is that when one measures such property, it sends the information to the other sock somehow, and it makes the state of the sock flip. So let's say...
So the only classical explanation we're in this setting where we have this uncertainty principle where we're saying that you can only know for sure either the sock's number of holes or the sock's colour. And then but we found that it's always correlated, whichever property, when we both look at the same property, it's always correlated. And then you're saying the only classical explanation for this would be if when I choose to look at number of holes, something then kind of propagates from me to you to tell your thing, like, she's chosen to look at number of holes, so...
Exactly. You need to conspire to get the same number of holes on the other side. Yeah. Exactly. And what is crucial about this is that it's independent of the separation of the two socks. All right? So then when you tie this together with the fact of the speed limit of propagation given by the speed of light, then you have then we call this that you have this non-local influence.
Because we could move
from one to the other
so far apart that between our measurements there isn't time for light to get from me to you, and then but the properties are still correlated, so this explanation doesn't work anymore that something went from that they conspired.
Exactly.
Yeah.
So they have an immediate influence over time from one sock to the other, let's say. All right.
Yeah.
However, this sometimes it's tied to say this is a very big misconception about quantum entanglement. What I'm going to say is that okay, then I can use quantum entanglement to send faster than light communication. So, because basically we prepare this quantum entangled state, I give it to you, you go to China, or whatever. Well, I should go to China. So I go to Hong Kong, you stay here, and then like you just measure in some way, and then like maybe we can use this influence so you can send me a signal to me. However, this is not possible. It's not possible to send signals because of this random nature of when you do the measurement. Things conspire, things turn out that you cannot send a signal that I can detect there. So I will just see a measurement, but I will know that if you would have measured in the same basis, we would get the same. But
where basis is the property that we're measuring.
Sorry, yeah.
So yeah.
Sorry, yeah.
Yeah.
But I
so
don't
if
know.
we measure the same property.
Exactly, but
yeah.
I don't know which property you have measured. So I cannot extract any information whatsoever.
Yeah.
About
so you only kind of notice this influence.
Yeah.
Apparent influence between.
You deduce the influence because of how.
When you know what property the other person measured.
Exactly.
And what outcome they got.
Exactly.
But without knowing what property they measured and what outcome they got, then, you kind of don't have anything extra. Like it could have just been a random thing. You don't have any, you can't deduce that there were any influences from anywhere else.
Exactly. So this is, we will be a bit pedantic, but it's a bit important. It's different to say that there are non-local influences as to say that there's no local signaling, where signaling is this idea that you can send some information or some message, or that you can change the physical property of your system elsewhere by you doing something here, that you could change the physical property of something.
So if we have two separated things and there was a way of doing something to this instantaneously or faster than light, being able to change an observable property of this one, then you could communicate. Right. If that could happen, then I could say, okay, well, I'm going to do one thing to say yes and another thing to say no, and this will do that to that one, and this will do that to that one.
Exactly.
But everyone agrees quantum mechanics doesn't work like that. We can't do that. Even with entanglement.
Exactly. Even with entanglement, you cannot send messages. To remote locations. By using this non-local influence.
Which is it's actually an exam question sometimes. Is like,
oh really?
Can you explain why? Or it's like, it'll give you some situation like Alice and Bob do this, this, and this. Explain whether Alice can now communicate to Bob faster than light, and the answer is always no, she can't, because the outcome is random, and that comes up in graduate quantum information courses sometimes. But
however, going back to Einstein. Einstein, what he thought is, okay, like he knew that, okay, I cannot send signals. However, what I do measure in the lab is something that exists, is something that is there. It's a click that I see in my screen or anything. It's the sock is there, let's say. And he thinks that the outcome of the experiment, let's say the fact that I am seeing this, is something physical, is something that exists on its own. All right. So then these influences for Einstein were very, very, very problematic, because you then did have this violation of the fact that you have something physical here, kind of like the glass of water before, that you do something to this glass of water, and then that will have an effect to whether this immediate effect on whether this glass of water will spill or not spill. So from Einstein, he was very concerned about this. So he proposed a solution is, okay, if you think that the explanation of this situation is only given by quantum mechanics, we run into this problem. This problem is completely unacceptable. Because
of having unobservable influences, immediate influences.
Exactly.
Yeah.
For Einstein, having something non-local was ridiculous to think about it, because basically all the history of physics that we explained before was converging towards the more local the explanation you have, the better model of reality you have.
It's like, look, we can introduce fields.
Exactly.
Look, we have special relativity and general relativity, and they're all nice and local.
Exactly.
Yeah.
So for him, it was like, this is just ridiculous. The fact to suggest that if I wave my arms here instantaneously in Andromeda, I don't know, so some atom will decay. It's like, the world clearly is not like that. So then what he proposed is that, okay, then basically what it can be truly be happening is that there are some other properties that are hidden that we cannot measure because technology does not permit us to zoom in into the electron as much to measure these properties, and maybe we can never measure them. That's why they are called hidden variables. And what he said is like, okay, if I have some hidden variables, maybe these hidden variables are the responsible for that when you prepare this entangled state, then it was predetermined already which answer would come up, let's say. So there is kind of like this extra element of conspiration with these hidden in the shadows hidden variables that would conspire so that your measurements would agree. That was kind of his proposed solution.
So the proposed solution is like, if we have these so we have these particles that interact and then we separate them, and somehow when they interacted, after they interact, there's now these hidden variables, hidden properties that we can't measure. Maybe we can never actually kind of access them, but they're what's determining that the particles will behave a certain way when, in terms of what they show when we measure them, when we measure the properties of either the holes in the socks or the colour of the socks. The hidden variables are going to tell us what they're going to make sure that the particles will always do the same thing without needing something to move between the particles, so without needing any unobservable influence or any influence of any kind to happen between them.
Exactly.
And so he was proposing this as, here's a way we can save locality is by introducing these hidden properties, hidden variables.
Exactly.
And maybe maybe we can save locality that way.
Exactly.
Yeah. And then so then what happened, so people thought this might be a possible explanation, but then Bell came along and kind of figured out, he did some calculations of if this really was the case, that there were these hidden properties, then the statistics of the measurements outcomes would behave in such a way that they violate this inequality that's known as Bell's inequality.
Exactly.
And then there were these Nobel Prize winning experiments done that actually implemented these experiments of doing all these measurements of entangled systems in the different properties and showing that they really do violate the inequalities, just as our quantum mechanics calculations tell us that they will.
Yep.
and then everyone was saying, well, Einstein was wrong.
Yeah.
So can you tell us a bit about what the assumptions of these tests that Bell came up with
Sure.
were, and then what proving that violation experimentally that he deduced would happen, what that's telling us about entanglement and these influences.
Sure. So basically what Bell did was to use very strong, rigorous mathematics. He was not trying to make physical arguments. What he was trying to make is like, okay, let's assume this is truly there are these hidden variables, all right, and that they have some probability distribution of happening, and now let's see if there are some bounds on, because basically we want to save locality. What he made was a model based on conditional probabilities. Maybe we're getting a bit too mathematical here.
I would say conditional probabilities are they're like where the probability of something depending on something else happening. Like
Exactly.
That's what you're calculating when you calculate a conditional probability.
Exactly.
Yeah.
So basically he put a bunch of very reasonable requirements. So basically is that the probability of Alice measuring 0, let's say, should only depend on the hidden variable, the fact that Alice has chosen to measure that property, and the initial state of the system, the initial configuration of the system. Like it should not depend on the outcome that Bob obtains, and it should not depend on the input that Bob gives, in the sense that in the choice of measurement of Bob.
Yeah. So those conditions make sure that we're keeping with this principle of there being nothing of the things that Bob is doing, so deciding which property to measure or getting a certain outcome, none of that is influencing Alice. That's kind of built into the assumptions.
Yep.
And then, it's constrained that Alice's measurement outcomes, probabilities can only depend on the hidden variable on her side. And
And then when you follow the math of conditional probabilities following this, these assumptions, what you end up seeing is that the overall probability distribution, we call it, so like the overall probability that Alice chooses to measure this property and obtains this result, together with Bob choosing to measure this property and obtaining this result, like we make a very long table of all the possibilities and we calculate all the probabilities, let's say. So that's what we call a probability distribution. Basically, that it had to take a very specific mathematical form. And then what Bell was able to construct is, he came up in a way to always sum together part of these probability distribution parts, and he would see that if the statistics of your experiment followed kind of this hidden variable model that is for local hidden variables, for a specific number that he designed, you would always get a value that at most 2, at most. But then he reproduced the same setup with a quantum particle, with quantum entanglement, etc. And then, then people saw that basically when you do it with a quantum particle, you don't get 2, you get 2 square root 2, which is larger than 2.
Yeah.
Therefore, what you end up seeing is that if the quantum mechanics prediction is correct, you should obtain, when you calculate this number in your experiment, you should obtain 2 square root of 2. Meanwhile, if you have a local hidden variable model, you should obtain something that is less or equal than 2. And then there's, as you said, like these experiments that they were done much later. I think they were done in the 80s, the 90s, and the 2000s, where they did these experiments with quantum particles, and they saw that you get 2 square root of 2.
Yeah, and showed that quantum mechanics really does go beyond whatever the upper limit is of what you'd get if you were doing this with a system described by these local hidden variables that were suggested as a way of saving the principle of locality.
Exactly. And I want to be a bit clear. When we say local hidden variables, I think it's well understood, which is like we are saying that there's some other extra variables that what quantum mechanics gives you that we cannot directly measure necessarily. And the term local, what does it mean is that these variables do not work kind of action at a distance, like in the sense that they are not able to influence one another instantaneously. Okay, so this is what local means here.
Yeah.
Okay.
Cool. So, and then, does the violation of Bell inequalities, so it's often said that it shows that local realism is not true, so either the universe is not local or not real in some sense of what the word realism means. Maybe we should first, talk about what the word realism refers to when people talk about it in this context.
Sure. Realism is very simple to define. It's just to say that things do exist in the universe.
Things exist.
Exactly. As we describe them in our pen and paper.
Yeah.
So, simple example, when somebody is studying electromagnetism, right? It is realist to believe that the electromagnetic field exists. So, a realist thinks that, okay, I have this model of reality and it's called there is an electric field, it moves in this way, etc., etc. The realist thinks that this model is represented in real life, let's say. So out in the universe there is something that behaves like the electromagnetic field. And in the context of quantum mechanics, when we say local realism, we need to be a bit careful because there's different notions of local realism. So the notion of local realism that Bell and Einstein initially, so in the examples that we have been talking about, is the following. Is the term realism is that the quantum mechanical description, let's say, it's real. So in quantum mechanics, maybe you've heard that there is this thing called wave function or quantum state. So a realist believes that the quantum state is something that exists. Okay, makes sense.
So that's like the thing that we use to mathematically describe how quantum systems behave is actually a real thing.
It's a real thing
in the world, like in the universe.
Exactly.
Yeah,
it's a real thing. Okay, and local, it just means that, how to put it? One second. So, the term local realism is that there are these things that exist, right? And that these things that exist, some of them you can localize them in space. So some of them you can talk of them, this is a property of this system that is here in Oxford and it's not of another system that is over there in Cambridge or whatever, right? So in the context of the Bell inequalities, these properties that we think that exist are the measurement outcomes. So the clicks of the detectors. These are quantum mechanical properties that we think that they exist, and we think they are physical in the sense that they are made of stuff in the universe. There's physical mechanisms and they are there and you can observe them and everything's there. And So in this sense that you have these elements and you want to give an explanation to them. So when we say that Bell's inequality violates local realism, is if you assume that these observations are something that exists in the universe, they exist alone and independent of anything else, and you want to give an account to them, in an account in such a way that is local, not only in the sense that you can talk about them independently of other things, but also that they cannot influence each other across space immediately. That's what we mean by local realism. So Bell inequality violation, what this proves is that the measurement outcomes behave in this way. So either they are not independent of anything else, either they are not real. This is difficult to challenge.
Yeah.
There's people who will challenge it.
Probably.
Yeah.
I agree with you though. I would like the universe to be real. But yeah.
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 Or the permanent vision is that they are non-local, in the sense that they can indeed influence each other, even though, as we said, I will not stop repeating, you cannot transmit information with them. But it's one of these three properties must be violated. And most people drop the third one, which is why, for sure, you guys have heard quantum mechanics is non-local, etc., etc. But what's referring is that if you have two electrons, you entangle them, they go away. Since my detector makes a click when the electron hits or doesn't hit, that is a physical thing that happens, that measurement outcome, and that the only reasonable explanation that we have for that is that this has influenced the click of the other electron in the other detector. That's why a lot of people claim that quantum physics is not local.
Which is pretty radical. So, can we save the principle of locality?
That's very good.
Does entanglement really force us down this road, or is there an alternative?
Well, maybe you have seen what I've hinted at. That there were another option.
Yeah.
Which is also radical, to be honest. Like,
there's no escaping being radical.
Yeah, no, like it's everything. It's kind of a peculiar phenomenon.
Yeah.
But I don't want to say weird, because there's a lot of peculiar phenomenons in physics, like Coriolis effect, like Magnus effect. Like there's a lot of effects in classical physics that are peculiar.
Yeah.
We just need to stop saying that this is weird and difficult to understand. No. If you study it carefully, you can understand it perfectly. Yeah. Okay?
You kind of... Yeah, it can be weird, but still, like, satisfactory, and still... You can avoid... you can get nice explanations that don't have internal contradictions, even if they're weird. And,
exactly.
Yeah, so what's this other radical
The radical option is just to consider that the clicks are not independent of everything else. So, specifically, you don't think that the clicks in themselves are physical. You just say that they are a symptom of a larger behavior that is going on. So, this is where we enter another interpretation, which is called the many worlds interpretation. You guys have heard of it.
And if you haven't, there's this kind of general idea of the commonly there's the Copenhagen interpretation of quantum mechanics, where people will say, if you observe a quantum system in superposition, if you observe Schrödinger's cat, it will collapse into being alive or dead. But in the many worlds theory, if you observe Schrödinger's cat, the cat is both alive and dead, and if you observe it, you become quantum entangled, so you become correlated with the cat, and then one version of you sees the cat alive, one version of you sees it dead, and that's why it's many worlds, because there's two versions of you.
Exactly.
So so there's this kind of theory of how measurement works.
And in this, when you use this theory of how measurement works, because here, as we explained the Bell experiment, the Bell scenario, you need to do a measurement and you need to choose where to measure, etc. So when you apply this theory of measurement to this scenario, what you see is that the outcome is kind of, as you were saying, the cat, that it's either dead or alive, but that the outcome is not unique, right? So that there is kind of a universe where I see my detector clicking, and there is another universe where I don't see the detector clicking. When we say universe, this is I think the term many worlds is bad, because what you would think is that, there is this whole immense universe here, and just by doing this tiny quantum thing, you create another one that are
like all
as huge, exactly,
somehow.
and it splits and like. No, I think it's much better to consider it kind of like many experiences. All right, like this one I explained to my mother. She's like, I thought you were against supernatural stuff, but okay. So I call it many experiences, and basically the idea is, no. Like there is single universe. Single universe. However, there is a version of me that's kind of like a ghost that I cannot talk to or touch or anything. Then when this quantum phenomena happens, we'll experience the detector clicking, and there is another me, let's say, that experience the detector not clicking. Does that make sense? But it's not that
they're both just as real as each other.
Exactly, they are both as real as each other, and also like they live in the same space. So it's much better to think of them as just different experiences that are happening simultaneously, rather than a new universe is born or something like that, because it's not. I think it's more accurate.
Yeah, it's like the same underlying system, then having two different experiences rather than
two different
becoming more
exactly
things.
Exactly.
Yeah
It's just that. So if you use that theory of measurement, then you see that the outcomes are no longer physical on their own, because they are just part of a bigger whole, so that you cannot break apart. All right. So then when you use this theory of measurement, you cannot apply Bell's theorem, because you cannot apply Bell's theorem in the sense that your new notion of local realism, it's different, because you are no longer considering the outcomes part of reality, or at least an indivisible part of reality. They are part of reality, but they are part of a bigger whole of reality, and that part of the bigger whole of reality is what you really need to describe in a local way.
So the issue is that
sense?
we can't treat those outcomes of the measurements as the kind of isolated system that we're looking at whether that can affect other things kind of thing.
Exactly.
That's kind of part of this bigger thing, because there's these multiple
outcomes,
versions and multiple experiences. And so now we need to consider that entire object as the thing that we're looking at, whether or not it can be influenced by other things, rather than just the thing that you'd see in one kind of branch of the world or in one of these
to put it into a bit more concrete manner, before we have talked that the Bell experiment basically is you have two electrons, you make them entangled somehow, then you separate them, right? And then you detect them, right? And we said basically in the Bell scenario, either you hit a click because the electron has hit the detector, or it has missed it, right? So in that scenario, right, what you are considering is that basically you are describing the behavior of the electron, right? So what you are really thinking is that is the electron, the movement of the electron, the position of the electron in this case, affecting the position of the other electron? Because the position of the electron in the end is what determines the click or not, right?
Yeah.
Right. However, in this interpretation that we are talking about, the many experiences, you don't talk about the click, because the click, it's not the whole experience of the electron. Does that make sense? So you want to talk about the electron, but now the electron has two experiences.
Yeah.
So you cannot isolate one of the two individually.
Yeah, I see what you're saying. So it's like you can't use the click as a proxy for describing the electron anymore, because there are actually, in this theory, there's now more aspects to the electron's behavior than just the click that you saw. So that click is no longer kind of uniquely telling you what that telling you the properties of that electron, because there's more to it now.
Exactly.
And so the click isn't enough anymore to be telling you that property, and you need to change the object that you're using to describe the electron's properties now, because the click is now insufficient.
Yeah, that's a very good summary.
Cool. Yeah, so that's the reason that in this view of the world, in this theory, we now can drop that assumption of the kind of clicks being the
proxy to talk about the existence of the electron, let's say. And now, basically, in this theory, and what has been seen in the recent years, this is very recent work, is that if you use the quantum mechanical, a certain quantum mechanical description of the electron, I mean, let's not get into details, but like, you can just use
deep dive.
Yeah, exactly. You can just use just normal quantum mechanics description of the electron, but you don't focus on this click as a proxy for talking about the electron. You see that all the properties, you can actually work out that all the properties of local realism that we described before, they are satisfied. So in the sense
just
that
in normal quantum mechanics, just if you if you kind of see it with this in mind and just write out what happens, you can see that these properties are satisfied just by normal standard quantum mechanics.
Exactly. So a bit the punchline is, if you talk about the whole electron with considering all the main experiences that can have when it interacts with a detector, you can have local realism. You can have local realism in this sense, that you can talk about a single electron alone, so that is localized, and that you can talk about the properties of this electron versus the properties of this other electron, let's say. So in that sense, it's local, in the sense that you can separate things into independent existences, let's say. Realist in the sense that you think that these electrons exist, that they are there, and that these properties are describable and they are there. And also the other notion of local realism, that is that this electron cannot instantaneously influence this other one. So you can have all of these three properties satisfied with standard quantum mechanics, without any hidden variables, without anything. You just need to pay a little price. Of course, nothing comes free. Which is that some of these properties are not directly measurable. But
so can you expand on that? So you said the punchline is we can have
local realism with usual quantum mechanics.
No influences at a distance.
No influences. Nothing spooky like that.
Yeah.
However, you need to pay a little bit of price, which is you can have two physical situations where any measurement, any set of measurements you do, it's the same. So let's say physical situation A, physical situation B. So you do all the measurements you can to situations A and B. and you obtain the same results for both, right? However, what you need to believe that exists in one and in the other may be different.
Can you say that again?
Yeah, sure. Sorry. So
we have these entangled
we have these
systems.
we have these entangled systems, right? But you can entangle a system using different processes, but you obtain the same state. You obtain the same result.
Yeah. So there's different.
Let's talk about light 1 second, because I am more used to light. So there is different ways that you can do entanglement using light. One is like you shine it through a crystal, and a physical process goes on, and then you shine a very powerful photon, and that photon is kind of split in two, right? And then you can measure everything about these two photons. They are entangled. Perfect. This is one way to create these photons. There is another way, which is you have kind of a material. You also shine some laser to the material. And it's kind of that. And then the atoms in the material react to this pulse of laser, and they also generate an entangled pair. Okay? So
two different ways of creating an entangled pair of photons of light particles.
Exactly. But let's say that you create the exactly same state. What do we mean? That however all the properties that you measure of these two photons will always agree, no matter how you produced this pair.
So there's no way. So from your measurements on this entangled pair, there's absolutely no way to figure out whether the experimenter in the lab prepared it using the was it like a beam splitter type thing you said?
Crystal or
crystal
or funny material.
Yeah. So there's no way from just looking at the entangled, from any measurements you do on the entangled pair, there's no way to figure out which way it was prepared.
Exactly.
Crystal, funny material.
Exactly.
Yeah.
So you cannot know. However, according to this theory that is local realistic, so it doesn't have the influence part, the physical properties that you need to track to each photon, and that you think that they exist because you are a realist, they are different. And the reasoning behind of why they should be different if they obtain the same outcomes, let's say, is because you generated these two pairs in a different way. So they had kind of like a different life experience in a way, let's say. So that is sometimes, not always, but sometimes it gets registered into the existence of that photon. And this is some physicists, this is a heavy price to pay, because this is something called the Leibniz rule, which is basically can be described as if it looks like a duck, it quacks like a duck, it walks like a duck, then it is a duck. So basically, if you have two things in the world that no matter what you do to them, they look exactly the same, they sound exactly the same, like any test you can do on them gives you the same result, you should consider them the same thing. Okay, but in this particular case, you are dropping this principle in favor of obtaining locality and saving locality. So then it's up to you if which of the two seems more weird to you, which of the two you prefer to work with.
Yeah. So there's this kind of question of is it too weird to have my description of these photons, of these entangled pairs, my description of it, to save locality, the description can depend on what this preparation method was of the funny material or the crystal.
Yeah.
Even though there's absolutely no way to figure out that difference from looking at these entangled particles. They're like, they look like a duck and they sound like a duck, even though they might have been prepared in a different way, and my description of it tells me they were prepared in a different way on the level of the description.
Yeah.
But on the level of measurements, it doesn't it doesn't show up.
It doesn't show up, I have to say, okay, let me defend it a bit.
Yeah.
It doesn't show up once they are already prepared, right?
Yeah.
However, if you are in a lab, you for sure know how you prepared your thing, so
but if you're in a lab,
it makes sense.
Yeah.
But if
and then you give it to someone else.
Exactly, if you feed that to somebody else, then like they cannot know. However, if there was a way for them to kind of go back and change something in the preparation method, so let's say that you feed it to somebody else and then they refeed it to you, so they are re-prepared again, right?
Sorry, you give it to someone else.
No, so there's two people.
Yeah.
The one that prepares the entangled pair and the one that receives it. So let's say the person that receives the pair then is able to then feed back to the preparing person. It's able to feed back to the preparing person something that would slightly change the preparation method. Slightly. Then, with this change, when you then refeed this to the person that obtains it, then you would see a difference between the two. So, what do I mean?
Okay, I'm in the lab.
Sorry, yeah.
I'm an experimental physicist. I'm in the lab.
You're in the lab.
I make an entangled pair using the crystal method.
Exactly. Yeah.
I send you the entangled pair, then you change.
Maybe I made it a bit too convoluted. The basic idea is we call it different methods of preparation because the crystal and the funny material, they operate differently under certain conditions. So they may agree on this specific configuration that you have inputted them, and then the output is the same. But for sure there is some input.
Right, I think I see.
You know what I mean?
Yeah, so you mean that that there's something else you could do, that you could put into that material that would give you, where you can tell the difference between.
Exactly.
If it was if it was the
one or the other.
One or the other. So if I'm using a mysterious method to create photons or something, and then I'm sending them to you, then that you could say, okay, well now I want to input, can you input something else in? And then the output would be different depending on which method I was using.
Exactly.
So it's just that in this particular case of this input always leads to that output for both ways of preparing. So you're kind of defending the fact that it does physically make a different. It is physically important.
Yeah, how you prepare.
That they were prepared in different physical ways.
And that it's true that you cannot tell the difference between the two by just measuring the output, let's say. But if you give me the two devices, let's say, I can play with them and I can fully characterize them. So then I can fully characterize my entangled pair when it comes out of one or when it comes out of the other. That's it's a defense. It's not super strong defense, so that it's not as painful. Let's say to
it doesn't kind of worry you.
Yeah, exactly. So it's not kind of like you're reducing to some mysterious thing that distinguishes two things that are completely indiscernible. It's like no, okay, well, they are not discernible in in the scenario where I only have the output, but they are discernible if you give me the whole process.
Yeah.
You give me the whole fabrication method.
Yeah. Yeah.
That's
It's like if you have like, because of the water, I'm thinking of like 2 taps, and like one of them either gives you water or juice, and one of them gives you water or like wine. Then if you just get water out of both, then you can't tell which one you have. But
Exactly.
if you instead look for either the juice or the wine, then you can tell. So it depends like what you put in, what you get out, and yeah.
Exactly.
Yeah. Okay, so this is kind of one thing which might, if someone wants to, this is kind of one potential critique of maybe the principle of locality isn't true because I want to keep this other principle.
Yep.
Do you think that's the main thing that worries people about whether the principle of locality really does hold, or do you think, what other kind of objections might there be to the principle of locality holding, or arguments for, this not being the satisfying explanation?
First of all, I want to specifically clarify that we are talking the principle of locality in the perspective of quantum physics and quantum foundations, because as we said, it's a very general principle, and different areas of physics may have different notions that we in a bit we can talk about. So one of the talking specifically about this principle of locality, principle of local realism in quantum physics. So this is a story that we have been talking about Bell and Einstein, etc. One of the main critiques is, this theory of measurement that we use, like this main experience theory, many words, I don't like it. I don't want to use that. I think that the world is classical at some level, that not everything can be explained through quantum mechanics. That, for example, this table, it's classical. And so that there's kind of a cut at some point where quantum mechanics stops being a good description of reality. So that is a criticism, because basically this theory of measurement, what it uses is that everything is made out of quantum particles, therefore everything is a big quantum mechanical system. When the electron interacts with a detector, what it's interacting is with another quantum mechanical system, so I can treat it as a quantum mechanical system. So this is what they are using. That's one of the strongest critiques, because in the end this is an interpretation, so you interpret what it appeals more to you, and whatever explanation you think is best. Right?
So that critique is, someone might say that they don't think that quantum mechanics, that we can use quantum mechanics to describe a measurement device, and therefore we don't end up with this many worlds theory, or whatever your preferred word for it is. And if there's some kind of, so there's objective collapse theories, for example, which say that they'll model a portion of the universe as some kind of classical way, or there's some threshold where something will collapse irreversibly into a single state, and then then you can't model measurement in the way that that you described earlier, in the way that allows you to kind of escape from the assumptions of Bell, that lead to the Bell's theorem. Maybe one interesting point is, the many worlds view kind of comes from applying quantum theory universally, so applying quantum mechanics to describe things at all levels, which kind of makes sense, because if microscopically everything's made up of quantum systems, then why would the whole thing be describable as a quantum system? And that's what we mean when we say we're applying quantum theory to the whole universal to everything, and measurement devices are being modelled as quantum systems. But there are different kind of viewpoints within that. Like many worlds is almost, I guess, one class of theories centered around the idea of there really being different physical versions of you that emerge when you do a measurement of a quantum system in a superposition. Do you have any comments about what are the other theories where quantum theory is also described as being universal? So in the sense that where you can treat the observer as a quantum system, but they're not necessarily leading to this many worlds view. Would you say that those theories in general also obey the principle of local realism in this sense, or I guess it depends on which of those we specialise to?
I think it just depends on which, because one of the central things in local realism is to just decide what do you think it exists. Right?
Yeah, because it's realism.
It's realism. And
we have to commit to something existing.
Exactly. And then that something existing having these properties of being talked independently and the fact that it cannot influence remotely, let's say. So it just depends on what they commit. Like what I can say is that if you commit that to the properties of the individual subsystems, so of these individual electrons that we have been talking about, then you save local realism. But then I would have to go on a list, let's say. Because, so for example, a lot of people, even within many worlds, like they commit to that what exists is the quantum state, it's not the quantum properties of the things. And the quantum state, it's kind of like the discussion that we were having before. It only cares about the outcomes of the experiments, not on the preparation methods. Meanwhile, the quantum properties, they do care about the preparation methods. So somebody who commits to only the outcomes and only on the quantum state, they would still believe that Bell theorem applies to them, probably. Or I don't know if they would believe that the Bell theorem applies to them, because like they still have multiple outcomes. But they would not have a super clear picture of how local realism is implemented or how it's safe.
So if it's kind of like saying if you have you have to fully commit to what you're saying exists in order to have a well-defined version of what local realism is, of what you're saying is true. When you're saying that the world is local realistic, you have to say what you're saying is existing.
Exactly. And in which way is local, and which is the mechanism that then explains entanglement. And and so even in this setting of treating everything fully quantum mechanically, you can still get kind of different disagreements over whether local realism holds, because someone might have a different might say depending on what object they are saying is the thing that exists. Exactly.
And I guess an example of that is the Bohmian interpretation, which people are working on, is non-local in the sense that the thing that is said to physically exist in that theory does allow these influences.
Exactly.
And which leads some people to then rule that interpretation out, because they're saying, nah, I want the principle of locality, and
you're not giving it to me. Exactly.
But others will drop other things in favour of this non-local theory.
Exactly. Basically, in the end, like I think our job as physicists is just to be very clear about what are the assumptions of each model. Try to be as much consistent as you can. And in the end, in the end, I will not fight about it. Let's say, like, I will not get into a bar fight with somebody who believes in a different interpretation, because in the end, we're all trying to just solve problems and to understand the world a bit better. And okay, I prefer to understand the world functions locally, because I think it just has value to then propose theories, because the history of physics basically proves this to me. But some other person might think, no, what actually has value is just focusing on the things that you can measure, and if you need to sacrifice locality, it's okay, because I understand better the model and the world, and it gives me better ideas to describe the problems that we don't know how to treat yet, thinking it like that. And I'm like, yeah, sure, go ahead. Like, as long as you are consistent and you are kind of not misleading people, and you are not suppressing other views, like, go ahead.
Yeah.
That's how I see it. And sometimes it's useful to just have different interpretations. So when you're doing calculations, for example, I don't use the full local realistic model. Like, if I need to know an outcome of an experiment, usually I would use kind of the projectors and Copenhagen interpretation, for example. So it just depends on the context.
Yeah. And so this discussion about non-locality in this Bell test entanglement setting comes up a lot in quantum information theory as a discipline. And as we mentioned, locality is important in lots of different areas of physics, and is maybe used in slightly different ways. So there's also there's the group of high energy physicists or particle physicists who look at locality in a different setting as part of what they're doing. And then there's people in condensed matter physics looking at kind of a different level of explanation of what's going on than in quantum information, where we're focusing on qubits and controlling information on this kind of abstract level. Do you have any comments on, just from your experience in the community, on how you think people in those different areas may use or understand locality in different ways from each other, or similar ways?
100%. Like, in the end, the theme is always kind of the same, but there are little subtleties between fields. So, for example, people who work on classical physics, let's say, on calculating trajectories of bullets, let's say, or let's say calculating trajectories of bullets. For them, locality is this thing that we describe with the class. It's like there's no discussion that the bullet exists. Like, that is a given, right? And for them, locality is just this fact that the interactions that describe the universe are kind of that you can only affect your neighbors, let's say. That is one aspect of it. Also, the aspect that, so first thing, you can only affect your neighbors. That is one level. Second thing is that in no way, shape, or form you can immediately affect somebody who's in a very remote area to you. And the individual existence there is kind of given, okay? But locality, it's position based in classical physics. So it's kind of, hey, have a space. So locality, it really means being in a single position. An object is in this position, and everything is thought in terms of the position and the distance. Let's say, right? Then there is the locality, kind of like in field theory, let's say, or quantum field theory, where locality, again, is position based. So basically what they postulate is that these fields that we talked way in the beginning, they exist, and what you want is that the ripple in the field in this point of space does not instantaneously affect some other ripple that might be far away. And this getting a bit mathematical, it's constrained by the possible evolutions of these fields. We say that the interactions need to be pointwise. So let's say that if you have a ripple here and a ripple here, you explicitly don't allow them to interact remotely in your model, let's say. So that's a way they think more about it. It's more a constraint on the possible dynamics or the possible interactions between your systems. So there is not as much discussion on what it exists and and this influence. It's kind of more let me restrict the possible ways these objects can move by saying every time if I want one to affect the other, they need to be at the same point in space. All right.
And it's quite clear cut in that sense that.
Sorry.
Yeah, it's quite clear cut.
Exactly.
There's this constraint.
100%.
And it's
in quantum field theory, so it has the word quantum. So a lot of people may think, well, you have the same problem. No, for them it's the same because you have space. So their vision is more from field theory in this sense that when you describe the possible movements of the fields, the interactions need to happen between ripples in the same point. So a ripple here cannot instantaneously affect the ripple. It needs to travel there and then they bounce on whatever effect happens, it happens. And then there is this odd one out of quantum theory, where in quantum theory we don't have in general position. What we do have, it's a big system that we cut it into subsystems, and sometimes we give person names to these subsystems. So usually Alice and Bob. And sometimes in our heads we think, okay, Alice is in some lab and Bob is in some other lab, right? But it's not in the math, it's not in the theory, it's not, hey, Alice is 10 meters away from Bob, right? So that's slightly different because our notion of locality is kind of subsystem based more than position based. Right? And since we don't have this position based notion, and also we do not have things that live in space and single points, our notion of locality it's never about you need to interact at the same point, right? Instead we replace it with you need the interactions to be sometimes you need the interactions to be between Alice and Bob when they are very close, or imagine that we have Alice, Bob and Charlie, okay, ABC. The theory allows you to have global interactions,
which is interactions on multiple systems.
Exactly. Because there is kind of let's say so we have three things here, but they are quite close, even though at their scale they look very far apart from each other. So we still want that a local change in A does not affect B or C, right? However, that doesn't prevent us from having a global interaction on them. So for example,
which can
I have my big hand and I smash this distance. I'm affecting all of three at once collectively, let's say. Okay, so that is another misconception about locality, that one thing is to prevent
something over here
instantaneously affecting something over there, with the fact that the evolution of the universe is such that you do not allow for this global behavior, that you want local interactions always describe the evolution of your universe. All right, so these are kind of the main differences. And the quantum case, it's kind of a generalization of the other two. So it's kind of an abstraction because you can also think position as subsystems of the whole. But sometimes there is kind of this, because you need to do this abstraction. Sometimes when you talk to people that work in the continuous, so they talk about these fields and these field theories. Since you have infinite points close to each other, this mathematically sometimes creates some confusions, because in our field we tend to work with A, B, C, D. So
these chunks.
Exactly, it's just big chunks, not things that are infinitesimally. That there's infinites of them and they are super close together. So sometimes for some particular effects, what in abstract quantum theory we call local, for them it's a bit too strong, because for them, like, it's like, well, but like my point here, I just want the interactions to be point particles. Like, I don't really care that there is kind of this chunk behavior between the two. But in the end, everything converges. You just need to be a bit careful.
Yeah. Cool. And as you mentioned at the beginning, kind of interested in gravity, and we have this big open problem in physics. It's kind of the big foundations of physics question of trying to combine our best theories of gravity with quantum mechanics, which leads to all these problems when we try and merge them, and that's the kind of problem of trying to find a theory of quantum gravity. And do you have any comments on what kind of role locality, local realism, these ideas play in the problem of trying to merge these theories together?
So I think my personal experience, or my personal opinion, let's say, is that the problem of quantum gravity, it's more a mathematical problem than a foundations problem. But still, it's a foundations problem. So there are some suggestions. So the situation basically is that general relativity, which is the best theory that we have for gravity, it's super local. It's very, very, very local. All the equations, you can talk about the geometry of a small region of space. You can, if a change happens here, it does not have an immediate effect anywhere else. The propagation of this effect, it's at the speed of light. That's why we can measure gravitational waves, which is the way like these effects are mediated, etc. So it's very local in a sense. However, at the same time, it has a single world. So it's that the idea is that you have single geometry for the whole universe. So you just have one world, let's say. And the problem, at least in foundations, is that when you look at quantum theory, is you need to choose. It's either you have a single world, but then you have non-locality, as we have explained, or you can have locality, no problem, but then you have more than one world.
Yeah.
So there's still a bit of clash. I'm betting more on the side of keeping everything local, and then we'll figure out the world thing. Yeah. Because it's just experiences, it's not a real world. So it's okay. But that's my perspective.
Yeah.
But yeah, this is basically the conflict. And some people think, no, what we need to try to do is to make general relativity non-local, so then we can couple it to quantum theory, because quantum theory is non-local as well. So there's proposals on the other side as well, but yeah, let's see which comes up with a better theory.
Yes, there's these different ways in which the theories are kind of incompatible, and by kind of molding them in different ways, trying to drop certain principles from some of them, we get different approaches to how we might be able to
understand
create a new theory.
Yeah, exactly. Yeah. Or to get inspired to get a new theory. But yeah. And there's also some other problems, but that even in general relativity, for example, like it's considered a very local theory, However, when you try to put it in the language of quantum theory, which is the language of observables and properties and measurements, and more this language than not like field and positions and coordinates, which is more the field theory language. You have there's a lot of debate on how to do that, and some people claim that you cannot have local observables in general relativity, for example. So then, like this locality that you have at the field theory level, when you want to transition to the language of quantum mechanics, some people claim that you lose it.
That you lose the
locality properties of general relativity. So that is also a problem.
Yeah.
Yep.
Yeah, interesting.
Yeah.
So, yeah, on the topic of kind of open problems and other, these interesting things to do with, around the topic of locality.
Yeah.
Could you tell us a bit about what kind of problems interested in you that, what kind of problems you found interesting that you looked into for your PhD research, and in general, what you think is interesting right now to do with locality and things?
Sure. So in my PhD, basically, I looked at this interpretation of how to save local realism in quantum theory, and I just wanted to make sure that it worked for all quantum systems, because it was developed only for qubits, let's say, which are the systems that are idealized, and it's the ones that we use to model quantum computation.
So I think of qubits kind of like Schrodinger's cat. You have your cat being alive or dead, or a superposition of dead and alive.
Yep.
The qubit is a kind of abstract version of a quantum system that can be in state 0, 1, or a superposition of 0 and 1, like the cat can be in superposition of alive and dead, and then we use qubits as our kind of building blocks of describing quantum systems on this abstract level of what states they can be in.
Exactly. So the first time you encounter this salvation or of local realism, like you read it and reread it because you have consumed a lot of articles that they claim the opposite. So you want to figure out where's the trick. Basically, it feels kind of a magic trick.
Yeah.
So then for the PhD, I was like, okay, maybe it just works because qubits are very idealized. They are too abstract, but when you apply it to quantum mechanical systems that we do think that represent the universe, so let's say electrons, photons, all of these things that we really believe they exist, not that they are abstractions,
not the abstract version.
Exactly, to talk about quantum computation, let's say. Maybe there the trick just fails.
So if we go from the kind of information level of describing what's going on to the particles level of describing what's going on, maybe something was slipped under.
Exactly.
Sleight of hand was done there.
Exactly. And I just wanted to understand it better, because in the end, if the role of saving local realism is to the realism part, let's say, like you should be focusing on the things you truly that you truly think that exist, right? But I saw that that you can actually still do it. You get somewhat a bit, let's say, it's not as neat, not exactly as neat, but overall it's you obtain the same fact that you can save local realism for fermions, bosons, anyons, any type of indistinguishable particle system that you can think of. So this is basically what I was interested in, what I looked at.
You showed it works.
Nice. It's very nice. I saw it works, so that's cool. My supervisors were happy. Imagine if they say that no. But yeah. But what I found very enlightening is that when using this way of thinking, of identifying these local elements that describe reality, and like think everything in terms of these local properties, that it was actually useful for not only for understanding things better, which is our job in quantum foundations, but also to find new mathematical structures within particular theories. So in particular, this maybe it's a bit there's a type of particle that people in condensed matter like. It's called anion, that it's kind of an electron but weirder. Because
weird electrons.
Exactly. Much weirder.
Yeah.
That it's very curious because mathematically the way they are described is through nice pictures, right? However, nice pictures are okay, but for some processes in physics, it's better to just have equations with letters than pictures. Yeah. All right. So basically, what we saw is that we could put those we could put those pictures into this language, the same language as the usual fermions and the usual bosons, and we could use some of the techniques that we know to solve physics problems using fermions and bosons to these weird fermions that are called ions. And this was thanks to thinking and identifying precisely which were these local properties that described the local realism behavior of these systems. So that was quite surprising, and we're very proud of it.
Yeah, so you kind of set out to see, does this local realism work on the level of the particles, not just on the information level? Then you were looking at these particular particles, so fermions, which electrons are an example of, and then bosons, and then these weird particles, the anions. Yeah. And then in trying to see if the local realistic, if they satisfy the local realism, you constructed this new way of describing the anions using equations rather than the pictures that were describing them. And so this was a kind of new description of these particles that you found using through the journey of trying to test the local realism on that level.
Yeah. So it was cool. It was curious to me that exactly that thinking in this way of identifying the local properties of systems and let's say the local elements of their existence could be helpful in general in theoretical physics, but it was surprising, but I don't know why it was surprising, because in the end it makes sense. If you understand something better,
then
you should be able to describe it a bit better. Exactly. But it was a nice side effect of the investigation.
That's very cool.
Yeah, thanks.
So I guess maybe we can kind of wrap up this part, and so taking a kind of conceptual step back, if we could just kind of summarize the overall message of what we've been discussing, what would you say is the overall, if someone was just going to watch this part, then what would you say is the overall message about entanglement and locality, or overall idea that you'd want to say?
Okay. let me think how to be concise. I would say maybe you have been told that quantum entanglement implies maybe you have been told that quantum entanglement implies no action at a distance, and that quantum mechanics is non-local. But that's only the case when you think that the measurement outcomes of your experiments you can isolate them, and there's something that they exist and they can influence each other. There is a way out. If you believe that the detector is also a quantum mechanical system and that it interacts with these entangled particles in a quantum way, then you can talk about all the properties of the quantum system, and not only about the detection of it, not only about the outcome, not only about the click. And that saves you from this Bell theorem.
Mm-hmm.
And you can reconstruct a very coherent, a very nice picture of quantum mechanics where everything is local, everything is very well understood. It has some caveats. You need to watch the rest of the video to understand the caveats. But overall, quantum mechanics can be considered local, and you can describe entanglement through just local interactions and local properties of the particles involved, and there's nothing particularly striking or spooky or weird about it. It's just, at least conceptually, it's just particles interacting in a local way. They change their properties. You just track the properties of the particles, and that's it.
So if you take into account the quantum behavior of the detectors of the entangled particles, and you take seriously what your mathematical description says about what exists, then you can have local realism.
Yeah.
And
in quantum mechanics, yeah.
Yeah,
Which is quite cool.
Yeah. It's very nice. Very, very satisfying. Yeah.
Yeah, also, then when you go to the lab or anything like that, and you are thinking in this way, everything makes much more sense. It's much better to just think, the photon is here, it's localized. Now, okay, this property has changed, so now the photon is kind of spread between the two arms, etc. So it's you just understand it in a much natural way for a physicist, especially if they are used to just using electromagnetism and because everything else in physics is local. So it just makes a lot of sense to just think like that. At least to me.
Yeah. We've covered a lot, so we can wrap this up. Thanks, Nicetu, for joining the podcast and for all these interesting ideas. It's really good to discuss these topics in detail that I think are very difficult to understand the subtleties of when you just do a standard undergraduate course in physics or a standard course in quantum mechanics, or just reading popular science and things. So it's really nice to talk to someone who's thought lots about these things and done research on these topics. So thanks for sharing your insights.
No worries.
And we'll put some suggested resources in the video description if you want to find out more about these topics.
And I just want to say thank you, Maria, for inviting me. It has been a very nice experience for me to talk about these topics in this way, because sometimes you just use a lot of technical language, and sometimes technical language kind of hides some concepts. So the fact to be able to explain them in a natural way so everybody can understand them, it also helps me understand them much better.
Yeah, same.
So thanks, and thanks for summarizing my points very nicely and very concisely. I understood more what I I think, thanks to you. So
Good.
thank you very, very much. And yeah, thanks for having me.
Great. Thank you all for watching, and see you next time for more fun discussions about foundations of quantum physics.
Bye.
Bye.
My mother will be proud. You want to do
Outro. Take 1. Take 2 of the intro. Take 3.
Like, I don't know if I should look the camera or look at you.
If you want to address the audience specifically, then you can be like, go read this paper if you're really interested in this. Like, you can, yeah.